Some people must have gotten blown away, didn't quite make it, and we just got here. Welcome. Thank you. Let's start with our usual tradition of introducing ourselves, and let's start over at this table here.
Jeff Sutton, Global Risk Consultants.
Tom Miller, Global Mechanical Contractors.
Tom Bruce.
The Governor's Council, and because Tom Brace is here and actually was in that meeting today, I would like to welcome Tom to the podium and tell us what has been happening with the council.
Well, I happen to be the vice chair of the Governor's Council, and the chairman was not able to be with us this morning, and that's Ted Sweet. So I was the one that chaired the meeting, and I wanted to point out first that Scott Futrell is your official representative, does a terrific job for us. We really appreciate it. Scott's here, and I believe Phil Ocker is the alternate when Scott cannot attend. Scott is on the executive committee and participates very, very faithfully. Let me hit just a couple of points. The Governor's Council did a white paper better than a year ago to create a forum for a statewide building code adoption. And we found, we put together a group, large group. One of those members agreed to carry the bill. We didn't get a lot of action this year, but it's still something that we're going to revisit. We would like to, the fire code is adopted statewide, but the building code, there are some major patches, if you will, that are not adopted. So our first goal is to see that that is the statewide standard. As some of you may know, there's Governor's Fire Service Day at the fair. That's August 24th. That's the largest single event of any activity at the fair in terms of a theme. Last year we actually had the governor for the first time in 9 years. It'll be at the Dan Patch Avenue in the Blue Ribbon area this year. We're going to move off Machinery Hill. We're looking for about 1,000 volunteers. It's a major, major activity. Those of you that follow the legislative session, and you remember the old homily about if a man loves the law and sausage, that you should never watch either one being made. One could argue that there was some truth to that this year. The fire safe cigarette bill passed. This is the fire-resistive cigarette. There's no such thing as a fire-safe cigarette. This is the cigarette that you put down in an ashtray and it goes out by itself. And we think that we're really proud of that. Some of us have been working on that bill since 1987, so it's time came. Statewide no smoking ban passed, effective October. Are there any smokers in this room? I'll put my hand up too. I tried to get an exemption for pipe smoking. It's not successful. I've used the analogy that cigarette smoking is a foul, filthy habit. Pipe smoking is an art form. I didn't carry the day. Last year, and I know that your state fire marshal, Jerry Roosevelt, told you about the fire safety account, did some fine-tuning and tweaking of that bill this year, but a whole new scenario to fund the state fire marshal's office and fire training. The money starts being collected July 1. So that's a very, very significant piece of legislation. The Gunflint Trail / Ham Lake fire is out for all intents and purposes. You recall the building sprinkler system, that's kind of, we're going to come up with a new name for that. But this is the yard pipe sprinkler mounted on top of the home, outside externally, that wet the roof and other surrounding areas. They had about a 95% success rate. What was interesting is that the lake was principal area they were drawing from was 18 inches down, and people had not gone out and checked their intakes, or had made provisions, to keep pumps running. The fire service, there was a number that responded from our area. There were a number of departments that instead of fighting fires were running around reconnecting and trying to get these systems up and working. And maybe a suggestion of an area is maybe someone from DNR or someone you might want to have at some later program area. I think you'd find it most interesting. The convective column was 50,000 feet in the air at one point. That's a tremendous plume. 90,000 acres burned in Minnesota, and 25,000 of that was in the blowdown area. So it is a misconception to say that it was the blowdown area that was burning exclusively. It was clearly much more than that. And as you know, the fire progressed into Canada. If I can leave a plug, any of you, and you don't have to be a good golfer, but the Minnesota 100 Club, and I think most of you know that group, it gives money to firefighters, police officers, public ambulance service folks that are killed or injured in the line of duty. We have a wonderful golf tournament at Hetrick Oaks on June 27th. Number of people in the council, including Scott, is going to play in it. If you have an interest in joining us, it's a great day. And as I say, you don't have to be a good golfer, but it goes to a great cause. We've paid out in the life of that Minnesota 100 Club over $300,000 to the families of firefighters and law enforcement officials that perished. So, sorry that Scott wasn't able to be with you here in person, but we close that we value his support, and we value the society's involvement in the Governor's Council. Thank you.
Thank you very much. We will start the program tonight. I've got some information that Paul handed me, and I just wanted to make sure that a lot of people here don't necessarily know Paul Rivers or Doug Rivers, even though both of them have been members of these associations in almost 30 years, since the early 70s. Paul Rivers is with the 3M Corporation. He's an advanced fire protection specialist. He actually has a Bachelor in Science in Fire Protection and Safety Engineering, and is a registered professional engineer. He's been in the fire protection industry for over 30 years, and for the last 17 years, new product development at 3M. And I think what has been exciting for those of us that have been around for a number of years is that Paul has arranged for us to be able to actually see some of those experiments at the 3M facilities. And I remember a few years ago that we looked at the Novec, if I get that right, system. And it was actually quite amazing that a lot of the codes that have been developed right here in Minnesota, and as a matter of fact, have been developed as a result of the work that Paul has done right in his own lab. He was awarded a patent, or 3M was awarded a patent for the development of the 3M Novec 1230 fire protection liquid. So I think that's a very significant development, again, that took place right here in Minnesota. And we don't often realize how much happens in this state that really affects the rest of the country. As a committee, he's also on various committees. He's a technical advisor, U.S. delegation to the ISO and Technical Committee of Gaseous Media for Fire Extinguishing Systems, a principal member of the NFPA 2001 Standards on Clean Agent Fire Extinguishing Systems. And that's what we're talking about tonight. So we have to, the man who's on the committee has written a lot of rules talking to us about how this came about and what is going on here. I think that's wonderful. Thank you very much for doing that, Paul. Associate member, Society of Fire Protection Engineers, and he has brought with him his assistant, specific mention, Todd Hetrick. And It says 3M Company internship student. You are there temporarily for now?
It is a temporary position, 17 months thus far.
That's a fairly lengthy temporary for some people a lifetime. He has a bachelor's in science, mechanical engineering, and he has a master's in science in fire protection engineering, actually from the Worcester Polytechnic Institute. So we have some experts here tonight to give us our program, and thank you very much for being here, and I'll vacate the podium, and it's up to you.
Thank you very much, Ed. Appreciate it. Now, Tom's been here about 17 months. He's by no means been here the longest. We've got a couple other guys who've been here at least 3 years, and they kind of make their career out of being an intern. He wants to get out of it here by the end of the year. He's doing his thesis on the topic that he's going to be speaking tonight, and so that's the reason why I wanted him to come and speak to it, because that work is ongoing, is going to continue on this summer as well. I'll discuss that. So, what I'm going to start off with, first of all, standard changes and regulatory trends affecting use of clean agents as Halon replacements. And the agenda that I'm going to have here is that talk about the industry activity and what's going on with NFPA standards. I mean, literally it's happening here in the next couple of weeks, particularly with the gases fire extinguishing committee, which encompasses NFPA 12A, which is Halon's, NFPA 12, CO2, and NFPA 2001. And so nothing's happening at Halon because that's basically, that's harvested, and eventually the property can go away, but we still got plenty of Halon system where there are definitely things going on. It's in NFPA 2001 and NFPA 12. And so in particular, talking about Class C, energy augmented combustion requirements, and also restrictions on CO2. Todd's going to then speak on room integrity and the testing that's been going on there. And then I'll go into, I'll take over them and go into some regulatory activity affecting the fire protection engineer, give a little background history on where we came from and why we're going where we are, and some clean energy development and climate change issues, especially as it relates to emissions from this area. And then I'll do a Q&A and wrap up. And Tom said something really good, about the sausage standards. If I kind of put it like, if you like the restaurant, don't look at the kitchen. And standards development is a lot like that. If you like it, don't look at the process involved, because it's oftentimes not history. Or not pretty. So, anyway, we have Class C gases, agents, that's what I'm going to talk about first, and give you a little background on that in terms of what's gone on with different industry, not just the fire protection industry, but also the actual end users, what's going on here. And then talk about some of the other standards that affect that, and then NFPA 2001 progression through the 90s to today. And in particular, talking about standards of what's called why is that there? I don't know why it's doing that, but standard is energy augmented combustion. That's the so-called Class C treatment. And NFPA 2001 and the ISO 14520, as Ed mentioned, by both those committees. In fact, the ISO committee is meeting in Boston next week. And then NFPA 2001, we've already had our final meeting last year, and the final cycle, and had the final vote actually in Boston in 2 weeks. So then we'll talk about the current NFPA 2001 activity and some of the future work that's going to be moving on with this. So energy augmented combustion, and the reason why I kind of talk about that is because energy augmented combustion really, some people equate it to Class C, but we never really had a good definition of what Class C is. Something that involves electrical energy. But energy augmented combustion can be a number of different things, not just electrical nature. You can have radiative energy that's added to it, that will affect the fire. You may have conductive energy that's in there, arcing and so forth. So really, we haven't had a real good definition of what Class C is. And as a result of that, we really kind of want to go away from that Class C definition and really talk about more in terms of energy augmented combustion. This is a flow diagram for a typical telecommunications switch. It's not, there's different ways that this can be done, different power supplies, maybe more or less. You may have with computer facilities, you may have different scenarios, but this is not unlike what you would normally have. This came from Belcor, actually. And you typically have a utility power feed with an auxiliary power supply and a transfer switch. That's a requirement of most any large facility like that. Goes into a main breaker, and then it rectifies down from the AC power coming into a 24 to 48 volt DC power supply, depending on the scheme that's used for that telecommunications switch. That then goes directly to the battery pack, and it continually charges that battery pack, and then goes into the main discharge control panel, from which it goes into the switch then. And then that is further breaker down to, again, all 24 or 48 volt DC. There's breaker from anywhere from 30 amps on down. And the important thing to know about all this is that there's no shut-off on this. This is all designed to stay operating. You want to keep that dial tone going. You want to keep the 911 calls coming when Target swipes their card. You want to make sure that dollars are transferred out of your account into theirs. And that's all important. It's all dollars or criticality, the criticality of this operation. And that's the thing that we don't really have an understanding of what we are doing here, in that what does that electrical energy, augmented combustion, how does that really, how does that affect those types of hazards? So that's what we're trying to get our arms around. We've been discussing it for a number of years, and it's been something that's been looked at in the electronics industry as well as the fire protection industry. You look at NFPA 75, this is back in the 1960s now. NFPA 75, which now is 13th edition as of 2003. That's fire protection for electronic computer systems. Remember, they have the big UNIVAC 1108 computers that filled up this entire room. Different scenarios than we have today. NFPA 12A was developed in 1968 in tentative form, and in 1972, I think it was, that it finally became a standard as for halogenated fire extinguishing agent systems. Belcor did a lot of work through the 70s and 80s. Cable flammability work, as the electronics industry progressed. In the 1990s, you had telecommunication group activities. You had AFC doing some combustibility work on equipment and so forth. You had the NEBS requirements for telecom. Formation in the late 90s of the NFPA 76 fire protection for telecommunications facilities. Which is in the second edition right now. And all that stuff, we're talking about combustibility, flammability, and so forth. The bottom line, there's no guidance on energy augmented fire scenarios and how to protect those. It's all passive protection. What do you do for suppression? We're using these gaseous agents, we're using sprinklers, we're using all kinds of things to protect them, but we really didn't have any guidance on it. We had no standards on this, and that was from, through that whole point in time. Look at NFPA 12A, which I said was the 5th, or the 8th, 10th edition, whatever it is right now, 2004. This is what's in the standard right now, NFPA 12A. Electrical and electronic hazards, these are the definition of the typical hazards. When it started out, it didn't even include electrical, but that's where it was used mostly, probably 90%. Electrical and electronics hazards, telecommunications, and then of course flammable combustion liquids and gases, particularly in the military applications, other high value assets, museums and so forth. So, but bottom line, after 30 years, there's no energy augmented combustion fire extinguishing design guidance that's been provided all the way through all that. This is the industry, this is fire protection, this is the end user. No standards. In NFPA 2001, through the 4th NFPA 2001 cycle that commenced in 2004, we've debated Class C definition. We've had no change. We have a definition now. The definition basically what comes out of NFPA 10, which is a fire that involves the electrical equipment where the electrical non-conductivity of the media is of importance. Absolutely nothing to do with fire. has to do with its kind of activity. So it's a lousy definition. That's why I'm saying we don't have a definition of Class C. Let's just call it energy alternative combustion. We do have energized fire data because that in the answer material that's been over the course of the last 8 years. A number of people have done a lot of work on that. In fact, we'll show you some examples here in a second. But basically, it's a conglomeration of other people, different people's ideas of what energy augmented combustion should be. Nothing standard, nothing worked on in a concerted effort as an industry. So there's no agreement on what an energy augmented combustion protocol would be. And so an EAC, Class C equals Class A, at least. That's the definition of it right now. It's the best we can do. What you do for a Class A is that's what you should do for Class C, at least. Not real good. Again, it gets back to this sausage definition of if you like sausage. You know? ISO 14520. This is the international standard. You know, a similar group of people, a lot of the same people at NFP 2001 from the United States are also on this committee as the technical advisory group for the U.S. And this is the part and parcel of the treatment of energy augmented combustion. You try to tell me if you can figure it out. Non-cellulose of Class A fuels, certain plastic fuel hazards, as defined as electronic type hazards. Involved with group power, data cables, computers, telecommunications. And at least they addressed, they put a definition of it as a little bit more than a Class A. Or at least differentiated from a Class A fuel or Class B fuel for that matter. And basically calling using 95% of the higher of the Class A or heptane Class B extinguishing test used under certain conditions, and these are the conditions: cable bundle trays, 4 to 9 or less, the density of the cable trays that you have, horizontal or vertical stacks of cable trays must be a certain distance apart, and so forth. Energized electrical equipment, greater than 5 kilowatts. If you look back at that last one there, the diagram I had, that was about 1.5 kilowatts. You know, 24 48 volt DC with 30 amp service. So that's basically, you do the math, it's about 1.4, 1.5 kilowatts. So this is a little bit higher. But that's basically the treatment for energized electrical scenarios. Now, this is an initial guidance differing from Class A or B fuels. Is it right? We don't know. That's half the problem. So, just to recap, NFPA 12A, no definition of what a Class C fire event or energy augmented combustion, no differentiating guidance. ISO 14520, no definition, but you do have differentiating guidance provided. NFPA 12, no definition, but there is some guidance provided. If you look at NFPA 12, you'll see that CO2 is pegged at about 50% concentration. I've checked back on it. I've not gotten a straight answer from the Bernie Bischoff from Chematron and other guys like that as to exactly how or why that definition or that guidance is provided. It just is. That's the way it's always done. So, to recap, the papers on energy augmented combustion, fire testing. There's been about 11 papers produced by manufacturers, about 16 or 17 papers in the last 10 years. On different scenarios, all good stuff. I mean, there's some smart people that have done this work. The National Institute for Standards and Technology, Japan Fire Institute as well. The consultant, Hughes Associates, has done some work. The general conclusion, design concentrations tend to be higher for all those scenarios. But we don't have any concerted industry on it. As far as what's happening in NFPA 2001, the committee action right now, what's going on, you can take notes for your dad, because he just went out. He's a man over 50 now, right? At 2005, the ROP, the Energy Augmented Combustion Subcommittee was formed to deal with this, reviewing the existing research that's been out there to date. In 2006, in the report on comments portion of the cycle, was basically review the data. The subcommittee proposed this guidance right here: Class C design, 2 times the Class A, or 1.5 times the Class B heptane coupler, whichever is higher, plus a 20% safety factor. and include that data in the annex. So it would be should data, not shall. What ultimately happened is that it was revised and passed in committee to a value of a Class C equals 1.6 times Class A as body text, providing explanatory material and removing all annex data. That last part is really good, but this part here didn't make a whole heck of a lot of sense. Yes?
Anything based on test data or just pulled out of?
This was somewhat that, it was based on test data. There was a review of all this, and it was based on what the work that was done. It kind of fell into the 1.6 range. That was about how it came up with it. Again, the sausage scenario. And that passed the final committee vote, and that was actually overwhelming vote from 20-something to 5 vote. So this is what happened then. An example of the selected FK 2001 agents. You see FK 5112, 125, 22078, and a couple of concentrations through 22878, and inert gas IG 541. You can see the Class A extinguishing concentrations that are from the UL testing for those particular agents for those scenarios, and then 1.6 times that in the Class A and the Class C design there. And you compare that with the no observed adverse effect level, and you can see why some people may be a little bit upset about it, or a little concerned about it. So, and that's basically where concerns happen, and as a result, what's going to happen now, which is a NIPMAN, and if anybody, does anybody know what a NIPMAN is? It's something out of NFPA now, one person now. No, Todd, you know it. But the NIPMAN is a notice of intent to make a motion. And it's something that must be submitted by someone who voted against the requirements in there. And that they would argue this, you're going to make a motion on the floor at NFPA 2001, at NFPA convention to debate this and try to get this turned back. And the decisions were, it's considered the decisions were premature, testing non-representative action with electronic hazards. It's debatable in some of it, but one of the main things was that in a lot of the tests they used nitro wire. Nitro wire, basically it's toaster wire, and that wire would take you up to 1800 degrees. Typical wire, copper wire, will degrade or break at 900 degrees. It would fail. So there's a disconnect there. So, but in any event, we don't have, like I talked about before, the industry does not have a concerted or an agreed upon test protocol on which to base our design criteria. Plus, also there was shall language in the body versus should annex material as guidance. And like I said, need for a standard test. So the current activity that's going on right now is that multiple NIPMANs have been filed by a number of companies. Alternative language was proposed by at least one of the submitters in lieu of the language voted on, which is not, it's a no-go. It's not going to happen because we're at the point now in the standard process where the standard doesn't change. It's either you agree with it or you pull it back and go back to the old wording. Two of the NIPMANs are stating just that scenario. Also, the Fire Suppression Systems Association Technical Committee is reviewing it and taking some action. At least some of the members are taking some action on it and doing some work. And there'll be a floor debate and a vote at NFPA in Boston here in 2 weeks. Then, whatever comes out of that will be published in fall of 2007 after a Standards Council vote in July. And then there's some future activities that will probably go into the next cycle, which would be additional energy augmented combustion. I don't want to say EAM, I'm not sure what that is. I'm dyslexic. Energy augmented combustion testing, and promotion of a laboratory technical development process to come up with an agreed upon test protocol, similar to what we did with Class A and Class B. So that's the Class C. Any questions on Class C for energy augmented combustion so far? You understand what's happening? Has anybody going to FPA in Boston? Gordy, you're in? Nobody else is? Okay. One other thing here, we're looking at the safety factors, and here's a comparison of the various agents that are in the standards right now. You see the Cupler heptane extinguishing concentration for those agents, and the Class A extinguishing concentration for those same agents. Do you see something about those different agents, comparing their agents that's different? Is that unusual for that?
227. Why is there 3?
Well, besides that,
You're going
227 has 3 tests. That's actually data. The 6.1 is the ISO data. Then the 5.8 to 5.25, those are both NFPA 2001 that are UL data. The thing about this here is that Halon 1301 and CO2, the Class A value is higher. All the clean agents, the Class A is lower. That's what competition will do for us. And because basically Halon, they didn't really push too terribly hard. If you look at the Class A values, you can probably take Halon down to less than 3, maybe 2.5% concentration. CO2 definitely as well, same thing. But with these, much testing went on over the last 10 years, 15 years, to take those concentrations and drive them down to the lowest common denominator. And that's basically what's occurred there. So what we have less margin for safety, less confidence by the standards organizations, UL and Factory Mutual, that they would work. That's why the criteria for passing the test were higher than they were for Halon and CO2. 30 seconds for extinguishing as opposed to 1 minute, for example, that type of thing. So we look at the comparison with NFPA design concentration, the ISO concentration for select agents here. Okay, this is for those who don't know the ASHRAE nomenclature here, this is FM200. This one here is FE25, some people may know as the Icaro. This is Intergen, and this is Novec 1230 fluid. Okay, so we have the comparison. You look at the NFPA design concentration is lower than the ISO design concentration, and that's because the two standards were supposed to have test protocols that were the same, but harmonized, if you will. But even with the same people on the committees, you can't get it, and you start getting politics involved with it in different countries and cultures mixing together. We couldn't get 2 protocols that were the same. So now you got the ISO standard has design concentrations that are significantly higher than what you have for NFPA design. What you're going to be most concerned about, what you'll see in here if you're using clean agents in the United States, is those concentrations there. As a minimum. So some of the activities that were looked at, the safety factor, what do you apply to those numbers? Some recommend the Class A extinguishing concentration be no lower than the heptane coupler value. That went away. Some recommend a 30% safety factor. That went away actually for a second cycle now. Room structural integrity validation. Should that be done by the professional engineer, or should it be done by you, the fire protection installer? Should you be responsible for that, or should that be from the PE?
Responsible for the testing, they're responsible for
Yeah, that's right. So there's a real debate going on about that. That gets into the PE licensing versus the NICET licensing and so forth. There's a lot of debate going on with that. Right now, going into the standard, there's a requirement that the fire protection contractor is going to be one that's going to be required to validate something he has absolutely nothing to do with. This room linkage, that's basically why Todd's doing the work that he's doing, is there's a lot of work going on to provide data, to give guidance for that, and to put what I believe is where this should go back to, which is a professional engineer. Revisit the room linkage. There's been testing done at the University of Maryland. And also, at 2007 testing, the OEM site is continuing. There's some work that was done last year, and also going to be this summer as well, actually in July, at Fight Corporation. Cup runner standardization, this is kind of a hobby of the standard. We do this every cycle for the last 15 years now. And we debate cup runners, so I think we might have it actually this year now we have round robin testing. And then continue with the energizing fire scenarios. So just to kind of recap, this is what you have for safety factors right now in the U.S. You have 120% of the extinguishing concentration, ISO is 130%. As compared with Halon, which is 160% as a minimum, and CO2, which is almost 200% minimum extinguishing concentration. And there's some issues associated with reliability, system design uncertainties, unbalanced systems, and so forth that provide some additional safety factors here. So, a little bit on CO2 here, then I'll turn it over to Todd for a second. Some history on CO2, what's going on, debating the safety issue with CO2. Is it safe or isn't it for use in total flooding applications? And some committee action that's going on. And also, again, another NIT has been filed. So what we have here is there was a report. This is all FPA 12 now, back from 2001. The FPA 12 is a report commissioned by EPA, citing liver fire deaths and talking about the safety issues of CO2 and some of the more technical aspects of what CO2 does to the body and so forth. But basically identifying the fact that there have been deaths from CO2 in total flooding applications where you haven't necessarily had that with other agents, and primarily in marine applications. In the news cycle for the committee, this is what EPA did. They came and presented to the committee proposing a limit of CO2, some sort of limit. They wanted to kind of negotiate with the committee. The committee basically thanked them very much for coming and presenting. It was a 5-hour presentation, which that's a little bit long. But in any event, the committee unanimously rejected it and told EPA to get out of town. Well, you don't do that to the EPA. And the reason why you don't do that to the EPA is because you've got to play by rules. They change the rules if they don't get their way. So the best thing that you must do is you must be negotiating with them to get what you want. If you think that CO2 is a real viable solution, you better negotiate with them. Well, the committee didn't do it. The committee was basically disbanded as a standing entity and became part of the Gaseous Fire Extinguishing Committee, which encompassed all three of those that I was talking about earlier. So what happened is EPA took a snap regulatory action to significantly limit CO2 in total flooding applications. They're actually looking to ban it completely, full stop. SNAP, by the way, stands for Significant New Alternatives Policy. That's the part of the Clean Air Act that EPA uses to analyze different Halon replacements and CFC replacements, those are depleting chemicals. So, Gordon, you're shaking your head.
I probably shouldn't ask the question, but what does EPA have to do with it?
That's a real great question. That's a real great question. The reason why they have something to do with it is because OSHA advocated their responsibility and right to regulate it. And being good bureaucrats, they look for ways of participating in your life. And as a result, that's what they do. So that's why EPA is involved with safety. Committee work in 2006, 2007. Some countering proposals were made by EPA and a consultant, Bob Wickham, and Tom Wysocki, who's chairman of NFPA 12, before it was switched around. Basically what happened is that the EPA went out. The committee put essential use limits that were voted on and accepted at that point in time. And those limits were upheld in RLC. It applies to total flooding only, not in local application. So, by the way, 3M supported the limits on total flooding from the standpoint that we actually pulled all of our total flooding systems out because of our concern for safety. We still have local application, but we had long ago in the process of pulling out our total flooding. So, Final accepted RLC language is as follows. And you look at it here, new total flooding carbon dioxide systems shall not be installed in normally occupied enclosures except as permitted where clean agent inerting concentrations, much higher concentrations, are required that results in the concentration above the low L, the lowest observed adverse effect level. That's a level that's higher. That's shown where an agent shows an adverse effect. Or the oxygen concentration is less than 8% in the case of inert gases. Fires involving energized electrical equipment up to 400 volts. Again, where did that come from? Don't know. It was pulled out of a hat. And grouped electrical cables for which gaseous alternative agents have not been successfully tested. Marine cargo holds is a takeout on this because there isn't a real good solution for that, and CO2 is shown it works well in that. No other clean agents have been used for that application. And then marine engine rooms, again, where a higher concentration is required. This is what it looks like in the final ROC, but down here, the substantiations, these provisions provide reasonable requirements for best essential use of carbon dioxide in normally occupied enclosures. These also resolve in part concerns related to a blanket prohibition on all new total flooding systems for the normally occupied spaces. In other words, it was finally what EPA wanted to do is get to a point where they didn't outright ban it, but they limited it to the point where its use is minimal in that application. Again, the current activity, the NIT ban was filed by Wysocki because he's the one that was wanting to keep CO2 there, and CO2, in his mind, with the data that he had, it was used safely, much safer than other industrial hazards that may be present. And what he wants to do is return to the existing treatment. And this is going to, again, be debated on the floor in NFPA in Boston to a standards council published in 2007, the fall of 2007. So that's a little update of what's going on with NFPA 2000 with gas and fire extinguishing standards. Any questions so far before I turn it over to Todd?
Was there a discussion, I think it was in the ISO Class A, where the new concentrations calculated were above the NOAA, was that right?
Yes, there were.
Was there a discussion about, okay, there's an observable adverse effect, but it's what it has to be to extinguish the fire? Is that essentially the...
Well, if it goes up above the NOAA, then some other requirements kick in. It has to do with something called the PBPK model. That is called the physiologically based pharmacokinetic model, which governs the exposure time for a particular agent. How long it can be used, how long the exposure time can be for that agent. The higher the concentration, the shorter that time limit would be until it gets to either low AL or a certain point, at which time you go past that point, it can no longer be used in occupied spaces. Hence, that's part of the reason why some of the agents had concern about treatment for Class C.
Was there, and I realize ISO and NFPA 2001 are different standards. The last time I looked at NFPA 2001 was some years ago, but at that time I didn't see anything in there about a post-discharge venting. Does either ISO or NFPA consider that after you've discharged a clean agent, does it require a certain HVAC interlock to dump the agent after the fire's been extinguished?
No, there isn't a specific requirement. There's some suggestions in the annex material on what to do, but there isn't a specific requirement for automatically venting a space post-fire or post-discharge. Okay? All right. Todd, you want to take over?
Thank you, Paul. So, as Paul introduced, this is my thesis body of work. It is an ongoing project. I'm presenting not quite everything to date tonight. I'm presenting essentially the American version of the presentation. I don't have any analysis done in this presentation on the ISO model, which is very different in a certain step if used improperly. So, knowing that, let's jump into it. The work, essentially, this is a validation study. In NFPA 2001 and ISO 14520, they have listed equations that you can use to, say, put in a certain concentration of agent to a certain size room and determine how long it's going to stay in there. Typically, we mandate a 10-minute hold time for that to provide both for extinguishment, initial extinguishment, and fire knockdown, and as well to wait for cool down so that ignition doesn't reoccur, as well to provide for the arrival of backup manual suppression. So the objective here, we're going to, once again, look at some of the existing calculation theory. This theory has existed in the form that I'll present it to you since the first version of NFPA 2001 came out in the original draft. We're looking at 4 different agents. HFC 227A or FM 200 actually was not done by the present research team. The results are subject to a little bit of question, slight uncertainty. You'll see towards the end that the results aren't quite as good, so we're going to be retesting that one pretty soon this summer. We're also looking at FK 5112 or Novak 1230, HFC 125 or the Icaro system, and Intergen or IG 541. And then, of course, we'll be concluding by comparing the results of our full-scale testing to the theory. So here, this is actually a Novak 1230 system. We've got a video of a discharge on the bottom. You can see that it's fairly turbulent, or at least aggressive for the most part. It's mixing well in the room as it gets in there. We're going to go ahead and make the first model assumption for the mathematics here and say that a homogeneous volume is formed. Thus, we don't have any agent settling to the bottom of the room. We've got an equal concentration throughout. We're also going to go ahead and assume down at the very bottom here that there's no diffusion of gas species. It may seem a little over the top, but as we see, it actually works pretty well. So essentially what we're going to assume is that once the agent goes in there and fresh air comes in on top, there's just no mixing. There's a sharp interface that forms. Thus, we're going to call this model that we're kind of building together here the sharp descending interface model. So what happens after the discharge? Well, we can compare it to the leaky bucket here. Essentially, we've got a gas volume inside the enclosure that's denser than the air outside. Due to that, there's a pressure disparity due to just the hydrostatic pressure that's produced by the column of agents sitting inside of the room. And due to that, it's going to leak out. All real-world enclosures have leakages. So I guess the real question now, and a lot of you are probably familiar with this once again, is that we've got all these structures that are already built, but we want to put clean agent systems in them afterwards. And even if we wanted to go about it the other way, it'd still be very difficult. We couldn't design a room and say, I want to have 1 square foot of leakage in it, and then hope that our construction men do exactly that. The bottom line is that we need to go in and measure it once the enclosure is existing. So here's just 2 example setups. We can take these racks of fans and install them into a door or a window and essentially pressurize or depressurize the enclosure by running them forward or reverse. And we can simultaneously measure the airflow rate through the fan, as well we can measure the pressure disparity between the inside to the outside of the enclosure. So using that, we can take our orifice flow equation. Now this is fairly rudimentary. You can pull it right out of Bernoulli's streamline equation. Essentially rooted there originally. And we already know our flow rate Q and our pressure differential just from the test. And then we've got some givens, our coefficient of discharge, empirically based. This has been found ahead of time. We also have our density, which is just the density of regular atmospheric air here. So essentially we can solve for our area, no problem. So now we know we've got this existing enclosure and we've got a leakage area for it, but that area doesn't have any location. It's essentially just floating out there. It could be anywhere around the enclosure. And we know that this clean agent is, well, because it's typically heavier than air except for in 1 or 2 select cases. For the most part, it's going to leak through the bottom of the enclosure. So what happens if this leakage is all on top of the enclosure? Nothing. We'll look at that in a moment, but essentially we need to know where it is. So for the purpose of the mathematical model, we're going to go ahead and make another assumption. We're going to say that the total leakage area exists in only 2 places. It needs to be divided between the 2. And so we're going to go ahead and introduce a variable. We're going to call it F, or the lower leakage fraction. And it's going to be a ratio of the leakage at the height of the ceiling to the total leakage area, or the leakage area lower plus leakage area up. Thus being just the ratio of that on the bottom versus that throughout the entire enclosure. So quick schematics, just to stimulate the thinking process here. If we have a leak only on the top of the enclosure, and we have, once again, no diffusion of gases, very important, or it would diffuse upwards and flow over through that crack, but essentially the whole time is infinitely long at this point in time. Now if it's on the bottom, if this was water, we'd see this kind of gurgling effect. But the mathematics don't care, they don't see that. So if it's all on the bottom of the room, once again, infinitely long whole time. So this input variable has incredibly sensitive result to the hold time that we're calculating. Whether it's one way or the other, it's essentially this gamut in between where we find we're closest to a worst case scenario where it's equally dispersed between the top and the bottom. So this is going to be our worst case assumption if we don't have further information. Of course, there are some extended test procedures that we can do. They take more time, they cost more money. Most people don't like to do them to determine exactly what this split is. The reason I'm spending so much time on this, though, is that I've been told by a couple of professionals in the field that a lot of door fan operators like to guesstimate what this value is. A dangerous practice, as you'll see. Nonetheless, we already know that it's the most sensitive input parameter that we have. So let's go ahead and move forward here, knowing that that's our worst case assumption. So the lower leakage fraction. We're going to go ahead and, just so that we can test during the actual experimental phase what this lower leakage fraction was, to go ahead and verify whether it's all right to guesstimate this value, we want to be able to measure it, but we've got to correlate it. We can't measure it directly. So what we can do is we can take our original flow equation, rearrange it a little bit. We'll solve for the leakage area A. Then we'll take our definition that we introduced for our lower leakage fraction F, and we'll just plug in the upper right equation to all of the areas. And when we simplify it, we have something right here that we'll be able to use, and I'll show you the results of this. But essentially, all that we're basing this on is two empirical values, the pressure differential at the lower, as well as the pressure differential at the upper, that being on top and below. And also the density of fresh air coming in through the upper versus the mixture density of ambient air and the agent going through lower. So here's a hydrostatic pressure profile, a little schematic just to kind of lay out exactly where the base of the model comes from. Once again, we've got leakage down low, leakage up high. We've got a sharp interface that forms, no diffusion of gases across it. We're assuming that fresh air comes in the top. Why does the fresh air come in? Well, we've got this column of air that's denser than that outside. It creates, just due to that, it creates a raised pressure right here that forces air out. We're assuming that this is an isothermal system, and thus we also have a fixed volume, so volume flows out, volume has to flow back in the top. It's a balance of air. We also have essentially our interface height, where you can see this represents the pressure increasing as you go down through the atmosphere. I'm sorry, this is the column of agent inside the room, and this is outside of the room. We've got a neutral plane height where the two pressures are equal inside and out. And that's essentially where we can relate this equation down here for the lower pressure differential and the upper pressure differential through our neutral plane height. Then we can cancel out that term and essentially solve for the interface height, H sub I. So if we do all that, we get this equation here. It's a first order differential equation. Use the first law of calculus and solve it. And we still have a little bit of work to do in order to compare a whole bunch of different tests where we are dealing with different leakage configurations, different agents, a couple different variables we can play with. We essentially want to render the governing theory dimensions so that we can take all these results, cram them down on one plot where they have axes that extend the same magnitude in each direction, and it's all directly comparable. So we go ahead and we introduce some characteristic quantities. We'll start with a characteristic drain rate. This is essentially just taking our regular gas flow through this equation and assuming that the driving force of the pressure differential is equal to a full enclosure worth of agent. And it results down to this. That way we can say, well, let's assume that the fastest force pushing agent out of the room would be if we assume it never leaves, and it's just that initial criterion. And then our characteristic drain time is going to be the entire volume of the enclosure divided by our characteristic drain rate. The volume cancels, we get units of seconds, and that would be our characteristic time. So if we divide our actual hold time by the characteristic time, we can render it dimensionless, substitute all this in, simplify, cancel it out, and what we get is this right here. Pretty simple equation. It's essentially 1 minus x squared. You can look at it that way. So it's a parabolic equation that's been shifted over one unit, and that's the theory that we're looking at. We've got 4 different dimensionless terms. Kind of makes sense. We can look at these and say, well, this is what should be governing the rate of descent. We've got a dimensionless hold time, which I've already introduced. We've got the ratio of the lower leakage to the upper leakage. This is, once again, essentially looking at our leakage split F. And we've got, once again, our dimensionless height and the ratio of our agent density to that of ambient air. So we can play around with our theory a little bit and We can see that our different agents, this would be FK5112 all the way over here. It's going to descend fastest. This is height, and this is time, essentially saying that the interface will fall with time through this height. And on the far right-hand side, IG541, you can see this agent doesn't actually have a problem with hold times. It's going to hold indefinitely. However, it does have another potential for damage to the enclosure, which is overpressurization. So there's a couple things to play with here. Of course, right now we're only looking at the hold times. So moving ahead here, essentially we've got our experimental enclosure graciously donated with helping hands from Fight Corporation down in Blue Springs, Missouri. A schematic on the right-hand side. In order to replicate the theory, we essentially have two rows of holes at the top and at the lower, different pressure transducers, temperature monitors, and such inside. Plenty of gas sampling as well. This is a tree of tubes at incremented heights that's constantly sucking gas out of the enclosure. So we're measuring our concentrations. Based on the type of agent, the type of equipment that we needed, the amount of manpower around, we were able to have different numbers of probes. So for our 4 different test agents, you can see that anywhere between 12 and 3 probes were able to be used. Each probe, based on what you're looking for, essentially only provides a single data point. So the surplus of instruments is very important. All these instruments were made back in the 70s, and they're hard to get a hold of. But nonetheless, here's a couple of them. You might have played with them. There's a Perco unit on the top, a turret unit on the lower right-hand side. The test setup there where we were working. Let's go ahead and look at some of the results. This is the pressure spike that we see. Like I said, IG541 has got an issue with overpressurization. This is actually the loosest enclosure for IG541. We had to use a pressure relief vent to protect the enclosure for most of the tests. FK5112, a negative spike, the lowest, HFC 22078, HFC 125. Why do we see a negative pressure spike? Well, for the most part, it's because these are very cold agents. They're cooling the air, especially for FK5112. It's a liquid, and it's evaporating. We're forcing it to by essentially pulverizing it through a nozzle at high pressure. When it evaporates, once again, it sucks a lot of heat out of the air, cools down the enclosure, shrinks the enclosure. We get a negative pressurization spike. At the end, though, this essentially is our agent discharge right here. This, again, is pressure versus time. Here we can barely even see our discharge, but throughout 4,000 seconds of time, this is essentially looking at the whole time. We've got 2 different pressure gauges here. This one, the low pressure, is at the top of the enclosure where there's a negative vacuum sucking fresh air into the room, positive pressure down low in the room. So this is the type of behavior that's actually driving the agent out of the room. That's just the raw force of it right there that we're looking at. Like I said, we derived this equation to look at what the empirical or the effective lower lead contraction was. So we can apply the equation that we had to charts such as this. You can see we have 4 probes for other ones. Nonetheless, we take our equation, we can plug in the value second by second that we collected for the upper and lower pressure differential. And it's beautiful. We can see, essentially, we've got a line that is centered right around 0.5, our worst case. This is exactly what we want to see. In this test, we had an equal number of open holes versus an equal number of lower holes. So, once again, if you're doing a test and getting a hold time and it's 8 minutes, you can't just go and say, well, let's go ahead and rerun that model with 0.4 and say it's going to work. Because the bottom line is that when we know what we're dealing with, the mathematics and the actual world work out exactly the way that we think they're going to. We can't just assume a fudge factor is appropriate. So once again, looking at this, we see essentially 0.5 on each one. Over here, we're down to 0.33. This actually had 1/4 openings on the bottom. We'd expect 0.25, but in reality, there's also uncontrollable leakages. We had holes that we drilled up top, but we also have cracks in the walls being closure. So once again, we expected this and are not surprised by it. So this is looking at the raw concentration data here. The general trend that you see is that discharge occurs. There's a spike in concentration of whatever particular agent we're dealing with. With time, as the interface begins to fall, one probe will see the interface pass. As time progresses, another probe sees it, and another, and another, and another. So essentially, we filter through this to pull out what our failure points are. The typical criterion is to say, look at about 75% or 80% of the initial concentration, somewhere right in there. Then we just draw a line and see where these lines cross. So let's go ahead and jump to the final analysis, at least for this presentation here. HFC 22070A, first off, we've got a nice grouping. It's a little more spread out than we'd like. Off to the right right-hand side, we can kind of say it's precisely inaccurate, and nonetheless, our errors are pretty high. Average error is 17.5, RMS 24.8. The average error kind of cancels out things where there's a positive and a negative, so for the most part, the cubic mean or the RMS error is what we want to pay attention to here. FK 5112, we've got more data points, 12 different probes, 5 tests per agent. That's constant, the number of tests at least. We're combining them all here. Different tests are colored by the luminosity, the shade of the dot. A lot better results, essentially just barely under 10% error. Very similar results. Well, we'll look at IG541 first here. You can see that this is actually not as good as we'd like. It appears as though the interface is falling faster than the theory would predict. This is a slight cause for alarm, certainly warrants further investigation. Once again, a little bit higher scattered here, 13.8 for the RMS error, HFC 125. But for the most part, we've apparently modeled it very nicely with some pretty drastic assumptions in the mathematics of the model. And if we go ahead and throw all those dots together, the cumulative error is 28.5. It's not horrible considering that some things in the fire protection world are acceptable level of error maybe between 30 and 200% depending on what we're modeling. So it's not horrible. To the eye it actually looks very good. So in brief review here, we've essentially rendered the theory dimensionless so we can compare a lot of different situations. Controlled our test enclosure, for the most part, I would say, to a sufficient level. I was very pleased with all the work that was done, and the numbers all came out pretty. And our dimensionless theory, compared to the results, sharp interface, for the most part, is providing a relatively good prediction of interface descent. Nonetheless, overly optimistic predictions for the inert gas agents. Sources of error, once again, still being considered. A couple of acknowledgements here. Ansel, Retrotech, Fight Corporation, SIVO, a lot of people in attendance. One international there as well, Bob Whiteley from the ISO community. All right. Any questions? Rover, please.
I guess I have a question on pressure, where Hetrick was high and the others were low.
Of course.
Don't the cylinders of the other cleaning agents have a super pressurization of nitrogen or something like that? I'm wondering why that didn't cause an overpressure.
Well, without flipping back a couple of slides, I was pointing out the largest of the pressure spikes. Most of the the hydrocarbons and fluoroketones, et cetera, would go down, and then they would also be followed by a smaller magnitude, but a positive pump towards the end. And that's essentially where you're seeing the extra nitrogen coming out. You're seeing the room reach a thermal equilibrium in the source.
So at first it's the liquid coming out, vaporizing, cooling.
Exactly.
And later on it's the gas.
Exactly. The reason I point that out is, as far as the structure is concerned, most people don't, to my knowledge, design them to hold pressure one way or another. A wall is just rated to, say, 5 psi, some other number. So whatever the largest spike is, that's essentially what we end up looking at. And another question, I believe?
Well, I have some comments on it and some questions.
Please, open it all.
I was actually involved with the installation of Halon back in the late 70s, early 80s, when we first got involved with the door fan test, being a replacement for the actual discharge of the R12, which was being used at that point in time. And just what I found interesting was just simply that, at that time, being fairly unsophisticated, we walked around with a smoke pencil and, oh, that's where the air is infiltrating, and we caught this, and we kept doing that for 3 or 4 hours until we got the room pretty well airtight based on the door fan test, etc. It's the whole purpose of all this work to essentially be able to model it without discharging anything of the actual test gases, one way or the other. Is that the intent of where you're going with all this 20 years later?
That's
20 years later?
That's certainly
It's been a while. But is that the idea?
I believe so. Of course, I haven't been around long enough to really say whether or not any simulant gases are being used. I was under the impression that pretty much we only do a door fan test now and there's no full-scale test discharges.
No,
except the novel design was made.
Yeah, no, I mean, I came in at the time when it was a full discharge test every single time. So they would roll all this R12 and then open the door and opt in the environment goes.
Yeah.
The Montreal Protocol in 1981, which put the end to some of my contracts, I must say. So that's why I remember, painfully, it cost me some money. But the short of it was is that that's when the door fan test first came into play. It was only being used to test houses and to see how much heat loss it was. And then somebody came up with a bright idea if we used that for the rooms. And we did, we came up with so many square inches of open space, et cetera, and then we went around and cocked everything until we got to a better number. And then we still did a full-scale test, dump test at that point in time, and proved actually what we had proven with the door fan. Now here we are 25 years later, or more than 25 years later, and you're basically now getting finally to the point where you're going to be proving theoretically and coming up with a mathematical model that is going to totally replace any kind of dump testing. I mean, it's already gone. I haven't been involved in
I
that.
can't really speak on that behalf. I can't. The ultimate goal, of course, would be just to do a fan test. My extended goal would be to do one of the lengthier fan tests, slightly more expensive and time-consuming, either using, say, above-ceiling neutralization or below-floor neutralization, or possibly to hang a tarp under the ceiling to temporarily seal leaks. When you go to that length, you can actually determine what this lower leakage split is. I've been told that when people guesstimate what the lower leakage split is, it's more of a European practice, or for at least jurisdictions under ISO 14520. In that code, they limit you to a value that has to be above 0.15 or it has to be less than 0.5. NFPA doesn't have any requirement or limitation. In fact, there's no reason that it couldn't be above 0.5. All of the mathematics work out beautifully for it. As I showed you in one diagram, if the flow is choked at the top or the floor, essentially the flow is less. So, nonetheless, though, in European communities, they will do a test, it doesn't work, and they've even called into a fellow that I've worked with on this project, and he sells them the fan units, and they'll tell them what they did, and then they'll tell them that, guess should be probably 0.15 since that's, a lower limitation, and then they'll go home. So that's a big problem if people were to do that. So I would recommend, once again, to do a lengthier fan test. Beyond that, though, I certainly hope no one's dumping any more, test gases.
Well, that use is the standard.
Yeah. Please.
Are you finding that your work is any different than the current door fan testing programs that are out there now? Or are you finding any deviations, or?
We used industry standard, as far as I know. We tested our enclosure before and after each test. So we're checking some variability from the method, things like this. But for the most part, this study essentially has shown us that the theory that we've been using since the first version of NFPA 2001, given that hopefully the fan procedure has not changed, that everything is really working out like clockwork. Nonetheless, what I began with and did not include in this presentation is that the ISO model is slightly different. They give you an extra variable to play with where you can predict the amount of concentration that has left the room over time. And if you do choose to use that variable, you get drastically flawed results. So the bigger project here is really to try and get the NFPA 2001 community to work with the ISO 14520 community and hopefully reach some sort of middle ground on some of this, because there are drastic deviations. In fact, the theory that I presented to you is the old version of NFPA. There's a new version that hasn't yet been published, but the new version will drop the amount of air quite a bit as well. So we're getting better, and they had to borrow that from ISO, but now ISO should probably borrow a little something from NFPA. And that's about where we are, and that's essentially the grand goal of this project. Any others?
I guess I have a question for Paul. I guess regarding this new 2001, this issue of increasing the design concentrations, is it of 3M's opinion that it's not a prudent decision right yet, it's a little premature, or do you not want to state what your opinion is?
I think, based on the way it went, it's premature.
Okay.
My personal feeling. I think that the best thing to have happen would be that for the industry is that we would have the industry guided by, through the same process that UL has, or Factory Mutual, or Southwest Research, where you have the group getting together and agreeing on a test protocol. whatever that may be. And it may ultimately come out to be Class A with Class C, I don't know. But we need to get the industry involved with that, not only the fire protection industry, but also the end users that are affected by this to come up to an agreement with that. So that's my personal feeling, because we did a lot of work on this, a number of manufacturers did work on this, but none of us intended to be an end all.
I've been getting a lot of phone calls about making sure I get there and vote this thing down, so.
I'm sure you have.
So
one thing that Todd mentioned here,
because for that exact case, they're using toaster wire for this. That's where this whole idea came from, right?
So,
not regular wire.
So, in any event, we'll get into regulatory issues in a second, but one thing that Todd mentioned is that we're trying to get the ISO committee, which predicts the inert gases very, very well for room integrity, whereas the NFPA predicts the halocarbon discharges very well. If we can get those two together, we have, in modified models appropriately, we'll have some good guidance for the future. And really, this is the very first time, and you're perceptive there, the very first time that we've really actually done full-scale testing as an industry to come up with an answer, try to, it really hasn't happened.
It moves at a snail pace, doesn't it?
Like I said, 20 years. And we'll talk about 20 years. Montreal Protocol. They were celebrating the 20th anniversary. Back when you were first doing your first discharge test was 1987. So we're celebrating the 20th anniversary. And that's led to the ban of CFCs and also Halons. I know a lot of you guys already know about this stuff, and so why is he talking about all this stuff? Well, I got method to my madness here for a second. But basically, we've gone through this process for 20 years, and you can see that this particular graph shows that ozone depletion was significant until we banned it in 1987. And it started to make a comeback once we stopped putting CFCs and halons into the atmosphere, and now we predict by mid-century we'll be back to normal, the ozone.
But wasn't that basically Freon and not Halon?
Yes.
95% of all the Halon ever produced is still in systems.
We'll talk about that in a second, because 15% of but they found 15% of the problem was halon, because halon is much more aggressive at depleting the ozone than the CFCs, on the order of magnitude more effective. So, what to do with the penguins down in South America, I'm not quite sure, that's where they were most effective. But the important thing to note is that we've been going at this for about 20 years now. We still haven't got rid of Halon. We still have an issue associated with that. We still got EPA with the SNAP program. We talked about that earlier, the Significant New Alternatives Policy, as part of the Clean Air Act, and it's qualifying with replacements and officially regulating ODSs. That program is pretty much morphed into climate change issues now, as we've slayed the ozone depletion dragon for the most part. And that SNAP program continues to this day. It started back in the late 80s, early 90s. And like Ronald Reagan says, that there's nothing closer to eternal life than a government program. And SNAP, I'm sure, is going to be here for a long time to come. So, halon, we banned it. It went in a lot of different directions. Recycled halon. We had not-in-kind solutions, sprinklers. We sold a lot. We sold a lot of control systems with sprinklers, where halon was used in the past, or competing with halon. Water mist, CO2, other no protection, prevention, and good sound practices. PFCs were used a little bit, and they were banned pretty much in the 90s, late 90s. Inert gases, we talked about that for a little bit. HFCs were pretty much the lion's share in the 1990s to replace halon. So what was the Montreal's effect on fire protection? Well, directly, we eliminated halon production. We didn't eliminate its use, we eliminated its production, right?
December 31st, 1992, at 11:59 p.m., Great Lakes Chemical and DuPont stopped manufacturing the product. Up until then, they were manufacturing 24/7. So introducing a lot of new technologies, the hydrochlorofluorocarbons, HCFCs, probably in your air conditioner at home, PFCs, HFCs, inert gases, fluoroketones, as total flooding gases, water mist, as sprinkler and gas alternatives, aerosols, they actually use rocket fuel to put out fires. You start a fire to put out a fire, some specialized applications. But the other thing is we got EPA in the fire protection business. That Campbell was known for under the tent. So this SNAP program took the place of OSHA. We were talking about that earlier. Why was EPA doing this? It's because OSHA advocated that responsibility. And also they're looking at regulating any Halon replacing those technology, whether it's replacing Halon or not. Figure it out. But the other thing that's happening is that environmental concerns are increasing as a significant decision driver. And why is that? Well, here's the reason why. This is what's in the marketplace today. It doesn't matter what you believe in it, doesn't matter what your political persuasion is, this is what your customers see. They see this kind of, it's not old stuff. This is very current stuff. And when they're seeing this kind of thing, and that's what's on the news every day, day in and day out, that's what the marketplace is saying. What's the Fed's doing? Our own senator, yesterday's paper, Cole backs a bill limiting emissions. There's 10 different senators that are doing this. They're Republican. Democrats, Republicans, it really doesn't matter. Doesn't matter what you believe, this is what's happening today. What's going to come out of it? I can't tell you. I really don't know. Nobody really knows for sure. But the United States, along with one other country, Australia, one other developed country, Australia, didn't sign the Kyoto Protocol. What's happening right now is you've got places like California and other states that are taking the matters in their own hands and they're making those decisions. And so those are the things that we have to concern ourselves, irrespective of what we believe. It's what our customers are seeing. And they have to reduce the risk not only to fire, but also to business long-term, and also to their property and equipment. But you look at, what's the contribution for HFCs and fire protection units? If you look at the U.S. in 2005, it's only 0.008%. What's the big deal about that? Why is this considered a problem? Why should it be a problem? It's essentially non-emissive. You just said yourself, 95% of the Halon is still in the can. So why would this be a problem? And the other thing is that HFCs using fire protection, they're very important in replacing Halon. Over the course of the last 20 years, we have used HFCs as one of the lion's share, the big circle down the bottom of that chart. And also industries are now invoking responsible use principles to reduce fire protection greenhouse gas emissions by reducing the annual emissions rate. Problem is fire protection HFCs versus the other industries. Those HFCs have global warming potentials that are 3,500 to 12,000 times that of CO2, much higher than the other industries that are being used. I'll show you a comparison in a second. Again, if it's not being emitted, who cares? Fire protection HFCs do not lead to an indirect benefit to CO2 emissions like for air conditioning and so forth, where you have an energy efficiency gains to account for the use of the product. And the other thing about fire protection HFCs is the installed base continues to grow, unlike greenhouse gas from other sectors. The other sectors, they use up those greenhouse gases and then they go away. Here, we continue to build the supply. Give you a comparison of the ones in red are fire protection. Here you got refrigeration market industry, the foam blowing and solvent industries. You can see the greenhouse gas and the global warming potential for the products that are used in fire protection are dramatically higher, in some cases orders of magnitude higher than what you have for the other products in here. I'll explain why that's significant to the regulators what's happening out in California here in a moment, but what other people are looking at, why the federal government is looking at this. the climate change policy over the last 15 years or so, 15 years, I guess. You have the United Nations Framework Convention on Climate Change. They came up with a commitment to stabilization of greenhouse gases. That's George Bush 1. Signed that one. Now in, where's it? In Kyoto Protocol, 1997 was recently ratified, actually last year. That takes care of CO2, methane, nitrous oxides, PFCs, HFCs, and sulfur hexafluoride. Sulfur hexafluoride is used in magnesium manufacturing and some heat transfer applications in electrical. But the commitment was to reduce greenhouse gas emissions, and that success is dependent on technology development in order to do that, and also looking at market-based mechanisms to reduce those reductions. In the EU, just back in 2005, they had what's called the F-gas regulations, basically taking it further than Kyoto and regulating it, but they were specifically targeting HFCs in those applications. There's specific recommendations for only HFCs, but it does include fire protection, including inspections, testing, training for the people that are over and above that for what would be considered sustainable applications or sustainable technologies. And there's also validations and whatnot. And most recently in our own country, the California AB 32, which is signed by, we saw Halon with his finger there, that was just recently enacted and signed into law in October. There's about at least 4 or 5 different states that are doing the same thing. And the California Air Resources Board is actively meeting at this point in time and looking for what we consider low-hanging fruit. And where is that low-hanging fruit? Remember back that small little sliver that was there? There isn't much to that. But when you had, back in the 1990s, you had PFCs, a small little sliver of the overall market. What did they do? They popped that right out. That was a win for them. What makes you think this is not going to happen to fire protection? So you have a card actively looking for that low-hanging fruit. Greenhouse gas emissions reporting is mandatory. You think manufacturers or companies want to be having that kind of scrutiny? Early action list is this year, 30th of June 2007. We want to have that early action list in place. And there was 4 additional western states that are taking similar action. Plus, you have about a dozen other states that attorneys general sued the EPA to enforce their responsibilities, their authority under the Clean Air Act. They're not doing that for other reasons, but that's what's going on here. And also, you saw that article with Norm Coleman in there. Big businesses in there asking the feds for greenhouse gas legislation because they're not sure what's going to happen in another year or so with a new election coming up. A lot of upset in the marketplace. The other thing that they're looking at as you look at reduction in greenhouse gas emissions, well, if you have Halon was taken out, PFCs are taken out with 30 to 50, 60% reduction in greenhouse gas to HFCs. If you get almost 100% reduction to sustainable technologies, ketones, inert gases, water mist, even sprinklers, probably even go back to CO2. What do you think they're going to do with the low-hanging fruit here? HFCs used in fire protection, where is it used? Where is it emitted? For suppression of a fire, do we have fugitive emissions from filling systems and so forth, maybe the manufacturing process? Per year, it's actually grown, but you're looking at 1 billion pounds of CO2 equivalent in a year alone. Doesn't sound like a whole heck of a lot, does it? But one thing about it is that the industry projects is that it's going to continue to grow. The emissions are going to continue to grow, and as that installed base continues to grow, so grows the emissions. This is right out of Verdonics paper that's presented here in 04. Using 1995 as the base, you can see any annual emissions rate you want to look at. They're both growing dramatically
This is just the actual HFC emissions from systems, fire protection systems in the United States. And so you can see it's growing dramatically, and that's based on the estimate that you're looking at.
But don't you have to compare the agent used as a fire suppression agent and its breakdown versus an accidental emission? I mean, I don't think you can put the two together.
Well, they actually do, because whatever is sold typically is sold for accidental emissions or for actual fire.
I understand, but is it not true that the alleged environmental damage is different from the accidental discharge on a non-fire scenario and a fire scenario?
Is the effect on the environment?
Right.
I have no idea. I'm not even addressing that particular thing or rendering an opinion on it, because it really doesn't matter. All I'm saying is what's happening in the industry today. You may very well be right, there's minimal to no effect. I can't answer whether there is or not, because I'm not an environmental scientist. All I'm telling you is what's happening in the industry today. The regulatory issues, the risk associated with using the technology. That's the main thing here. Especially when you look at this graph here. Now, what I want you to look at is the first four here right now. Forget the tall one for a second. Look at the fire protection sector. These are actual emissions. Assuming a 3% fire protection emission, you can use whatever you want. It's on the order of what you have for aluminum production, semiconductor manufacturing, and magnesium production. All three of those industries right now are on a phase-out schedule for greenhouse gases. They're going to eliminate them by 2010. Fire protection has no phase-out. They have responsible use. There's emissions reduction programs. You got HARP, you got FSSA, you got a number of NAFED, FEMA, all are part of reducing emissions. But even with that, voluntary emissions reductions are going on, emissions are there, they're positive, they're continuing to grow, and these are all phasing out. So the regulators look at, why are these guys not phasing out? They got alternatives. You just saw all those other alternatives are there. Why are they going to go after that? Then you look at the fire protection installed base that's there now, and that continues to grow. Now, CO2 equivalent basis, that's shown here. That's important, I'll show you in a second row. Because policymakers, like I said before, they have no indication that the fire protection industry is taking care of their own issues, that they're actively reducing those emissions in a very real way, like those other industries. So they look at those other industries, and that's what's happening. And even at the annual emissions rate, the absolute fire protection emissions will continue to grow proportionally with the installed base. As long as that installed base continues to grow, those emissions continue to grow. You look at with the current policy that we have in place today, global fire protection, HFCs will grow from 13,000 to 63,000 tons in the next 7 years. Look at California alone. If an estimated 15% of the U.S. installed base of HFC fire protection is in California, that's not unusual or not a bad assumption because of how big California is. It's estimated that approximately 7.5 million tons of carbon dioxide equivalent would be emitted there. And it's a portion of that amount. That's what's stored there. So, and the fact is that the voluntary codes of practice don't include text encouraging selection of fire protection technologies with the lowest climate impact. Water mist, inert gases, whatever. You don't include that. So the only meaningful way of reducing greenhouse gas emissions from the fire protection sector is to slow and eventually stop the growth of the installed base of HFCs. It's the only way to do it. Otherwise, it's going to continue to grow. The regulators see that. Just to put it in real terms for you, you look at an average size HFC system, say 350 kilograms, a GWP at 2,900, that's pretty average for them. This is what your greenhouse gas emissions per discharge, if you were to discharge that agent.
The 1.27 times 10 to the minus third millions of metric tons of carbon dioxide equivalent. Compare that with a sustainable product, orders of magnitude less, about 4 orders of magnitude less than that, with 400 kilograms of that alternative GWP of 1. Again, that's the worst case scenario for sustainable alternatives. You just saw all those other alternatives over there. So for HFCs, put it in real terms, what does that really mean? That means that you have emissions equivalent to 1 million kilograms of CO2 from one system. 1 million kilograms of CO2. That's the same equivalent emissions as you'll have from 211 U.S. cars for 1 year. One system. That's the difference. You look at the sustainable alternative, emissions from one system is 401 kilograms. That's 0.07 cars per year. Or if you want to put it in real terms, who said that they work around on a farm? The emissions from one cow for 1 month. All right? That puts it in real terms. That's a huge difference. That's what the regulators look at. They say, this is a real win. This industry, we can grab that right now. So what do you want to specify? So, just to wrap up here, the policymakers, regulators, experts were charged with reducing risk in fire protection, not only from fire, but also, from the other aspects that deal with it. We're actually in this because of the environment. That's the reason why we're here with Halon. It hasn't changed in 20 years. So we need to find ways of meeting the Montreal Protocol commitments without growing emissions of greenhouse gases and growing that installed base that will cause those emissions to grow. And not creating a future base similar to what we have with Halon today. Tom said we have 95%. I'd say it's probably less than that because we're using quite a bit of it over in Iraq and such places. But it's still there. And what do we do with it? Over in Europe, it's considered a hazardous waste. They're burning it in Australia. So, and how do we not add another environmental concern on top of what we already have? How do we not forget history? Where policymakers see is that sustainable technologies exist to reduce that risk. And so, I do have one thing. I didn't want to have a big sales job on it, but I do have to have one slide to show you something that has come up that's different from anybody else that in response to this. And the product that we have, over 1230 fluid, has a warranty for the product, an environmental warranty. When you go over 1230 fluid, if it's banned or restricted and used as a fire protection agent due to global warming or ozone depletion, 3 will refund the price for the product. And the warranty is good for 20 years, because that's all the father lawyers will allow us to do. But it's also a typical lifetime of the system, according to our OEM partners. You have to register with the system with 3M, and the system's online, very easy to do. As a distributor, as a specifier, you can specify that in. You can work with your end user to do that. It takes about 5 minutes to do.
Hey, Paul, is that from all that CE4 Ken put in?
Yeah. This is built in 1234. But I'll talk to you about it. So that's basically what it is. Do you have any questions?
So to remind us again, we looked at this NOVA a couple of years ago when we put on a demonstration. But if I remember correctly from that presentation, that particular liquid is environmentally safe, correct?
That actually was one that was a comparison. But that was also, and that's one alternative to Halon, it's one alternative to HFCs. Like I said, there are a number of alternatives that are there. You have water mist, there's a number of manufacturers there, all the manufacturers are using water mist, they're using inert gases, they're using a number of different technologies. As an in-kind replacement, yes, that's a sustainable alternative to HFCs and Halon. As an in-kind Halon replacement, yes.
I also, from what I remember, you need a slightly higher volume, slightly one more bottle out of 4 or something, including the Novak versus Halon. So is it actually a possibility of evacuating the Halon, recapturing it, and replacing it? There is the same system.
Yeah, you're looking for a drop-in replacement. There is no drop-in replacement. And by the way, it's probably going like 2 bottles to 1 for Halon, for Halon 1234. I mean, some of them more, some of them less, but basically that's about what you're looking at. But none of these products will replace Halon pound for pound or system. You might be able to use some of the piping as a system for any of these agents. There's one system that uses a bank of nitrogen bottles that push the agent on what's called a piston flow arrangement. Fenwell has that, and they are able to use the existing piping, change the nozzles, put a different special nozzle on it. Seabolt Systems has a 500 PSI system that they are able to use the existing piping in certain scenarios. But for the most part, you're not going to be able to drop in another agent to replace it.
It can be recovered, though. I mean, for a while, the service stations were basically evacuating the systems in cars, the 10 pounds or 12 pounds that were in there, were basically just recapturing them.
Yeah, and we are recovering, we're recapturing recycling alternatives, we're recycling Halon, we're recycling the alternatives. But the important thing to understand is that there is no take-back program that takes a system out of the marketplace and destroys it and it no longer exists. Eventually, everything that's put in systems now will be emitted eventually. With a positive emission rate from these systems, you will eventually emit everything.
So at what point is there no further emission from fire-rated systems?
There isn't. That's what I'm saying. There is no point where you're going to have no emission. It's going to be emitted eventually. Based on the data that's presented, this is UNEP data, IPCC data that we just saw. So, Tom.
Well, a comment and a question. It's a masterful presentation. It appears to a layperson that it's an incredible sea change that is being proposed. It reminds one of a steel worker that's leaning into the wind, high above the ground, and all of a sudden the wind direction changes. Some of us have been an advocate of Halon, ruled the day that it was banned. I've watched an iteration of other fixes, if you will, for an uneducated term. Other uses, never quite as good as Halon, and now the presentation is 25, 30 years later, wherever you want to go. We've got something that sounds quite simple and quite basic, and we've kind of gone back and we've changed the direction. Now, that's an oversimplification, I understand. But if water mist systems, as an example, are capable of doing what you argue can do, why in the hell weren't we using those 20 years ago? Because that technology was pretty much there 20 years ago.
It's probably there 40 or 50 years ago.
Okay.
But it wasn't done because there are easier technologies to use. Halon being one of them, CO2 being another.
Easier.
Those applications. And sprinklers, frankly, they're cheap. They're easy for the vast majority of the applications. If you can use a sprinkler system, you probably should. That's probably the most economical and reliable fire protection that we have today. And for most applications, if the criticality is a concern there, you can't use sprinklers.
Right.
You got to use
Something
these
else.
alternatives.
Something else.
Yeah, gaseous alternative. That's where gaseous alternatives are used.
Has anybody argued the point, though, that an unchecked fire is also an environmental hazard?
Absolutely.
And you want to talk about emissions, and so you want to talk about runoff in terms of water suppression by fire departments?
I don't disagree with you.
I'm not hearing that argument coming from our environmental brothers and sisters.
No, you aren't. It's not a politically correct thing to do. I mean, we argued the notion on phone many times, let's get the fire out, instead of let that tanker burn. AFFF, ATC, same exact argument. The point that I was trying to make is, again, it doesn't really matter what we believe, doesn't matter whether we are a card-carrying member of Greenpeace or an advocate of Dick Cheney. It doesn't really matter. It's in the marketplace today. That's something that we have to deal with. And when we're specifying fire protection, when we're making expensive, long-term decisions for our clients, we have to take that into consideration. I wish I could say it was just fire protection would be easy, but it's not. Environmental, remember I said EPA got into the fire protection industry, the Campbell's nose went to a 10. It's there, we got to deal with it.
How purchasing carbon offsets?
Pardon me?
Well, purchasing carbon offsets for all those
Systems.
Yeah, I didn't even want to get into that, but that's something that's being, that's definitely a part of it. That's part of the market-based mechanism I mentioned. You know, purchasing carbons, Al Gore's purchasing, other people.
Big way.
Yeah, that's right, in big way. He is. There's actually trading, British Petroleum does trading within their own divisions. They have a trading mechanism, trading scheme going on. So, something for you to consider.
Very good.
Okay? Any other questions? Thank you for your attention.
Well, I would say once again, it's always amazing to me how much is going on that in normal life you don't really think about. You deal with that every day, we deal with other issues, but this is why we have our meetings on a monthly basis where people bring out these different issues, and it's, for those of us who put these slideshows together, it's a tremendous amount of work to put this together, just to put on an almost hour-and-a-half long presentation. No, that's fine. I was not criticizing you. Obviously, you've helped the public here. But this is absolutely tremendous. Thank you very much for all the time and effort you put into it. It was very interesting, the thesis that you're working on in your paper. I can see that this is all going to come to some conclusion sooner or later. We won't be around to see it. You will be. I hope. If it takes another 20 or 30 years. But please leave your name tags in the bag when you leave. We'll have the next meeting probably in September. We haven't quite figured out what that's going to be. But thank you very much for the presentation, and thank you all for coming, and it was once again very interesting. Thank you.